I want to talk a little bit about error handling and exceptions. Now, when I started ThinkCell, we had to think about, well, first of all, which programming language do we use? We use C++, okay. But how do we handle errors? There are so many API calls that fail, or could potentially fail. And there are asserts that could fail. And I have to write so much error handling code. And which code do I write? I kind of didn't know what to do. And we had to think about what we did, what we wanted to do. And I want to tell you what we did. So, first of all, if you're talking about error handling and exceptions, there are a few ways to get errors out of functions. And really it depends on what kind of API you are using. So you can use return values. Is the F open? Did this work? It's okay. No, if it's not okay, then you have to do something. You can't use this for constructors. Here, return values. Because constructors don't have return values. Okay. Now you can have out parameters. You can say, oh, this is okay. Well, you have an out parameter down here, and this you can actually use for constructors. Now, both kind of clutters the code with all kinds of checks. Is that okay? Is that okay? And users can also forget to check. Okay. Then there's this thing about you can have a status. That's an internal state in the thing that you are dealing with. And it kind of says, oh, I got an error that whenever it encounters a failure. This is actually not bad. This is good because you got a single control path. You at the very end, you find out, well, did this all work that I did? And this is good if the checking at the very end is enough. For example, when you're writing a file, okay? I mean, if all your writes go into a garbage can, it's not what you want, but you can delay finding out until the very end, okay? So, and this is hopefully not going to happen so often, so you're not wasting too much effort writing a file that's already full, where the disk's already full. But you can just keep writing. At the end, you find out is it okay or not. Otherwise, you have to check it. And stdfstream actually supports status, which is nice. So this is not really a new idea. And of course, then there are exceptions. So what about exceptions? Well, first of all, I hope you know that you should always catch exceptions not by value, but by reference. Okay? Clear? Why? Well, otherwise you get slicing. So you have a B that derives from an A, and you're throwing the B here, and you're catching an A. Now, maybe you throw a B sometimes, or you're throwing an A sometimes. Something here inside here throws B's and A's, and you're catching A. Then the B gets copied into your A, and in the process gets sliced. That's a general problem of C++. You kind of cut the end of your B, and only what's left, only the A, gets copied into your object. And this invokes a copy. Well, the copy may throw itself, produces an exception. That's going to terminate your program right there. And also you're leaving, if B has virtual functions, well, you just lost it because you copied the stuff into an A, and the virtual functions they're gone. Now, when you write throw, this actually throws the original B, because somewhere in the system, the B is still squirreled away, and when you say throw semicolon, it throws the original exception. Okay. Now, I don't like exceptions so much either. They are practical, yes, where you really want them. But it's kind of, right now, it's kind of like you treat exceptions like the silver bullet of error handling, right? Everything throws and exceptions come out at every spot, and it's all a bit messy. Well, why is it a bit messy? So you have something like this, right? You have to increase the int I, and if I equals 3, you just throw hello, and here you catch it, and it falls down here, and here you output hello if you threw an exception. Okay, fine. Now, what does this equate to when I look at it? Well, it creates a lot of code paths. Let's look at the equivalent code. Basically, it says if 3 is I, then you say, oh, my exception is hello, and go to exception, right? Oh, we have an exception. We have to skip this part. You have to create a new code path that goes down here, and we have to somehow return. Doesn't really, we would kind of return nothing, except can't really do that in C++, but it's kind of this exception special return. And then here you have this, if this creates an exception, then again you have to go to exception, and there we actually output our exception. For people who really, really like exceptions, this may seem like heresy, right? So, but we say, no, there's not really a code path. This is just how we process exceptions. But still, I mean, this is factually a code path. And it does create lots of different code paths. And people may say, yes, it does create code paths. But you know what? We're writing exception-safe code. Please, I mean, where have you been? I mean, of course you write exception-safe code. I was like, well, are you really writing exception-safe code? So this was basically the question. Am I going to write everything exception-safe? I mean, let's look at what exception safety really gives you. Okay, when you're writing all the code exception-safe. Well, of course, if you can write the code so that it never fails, well, you don't have a problem, right? We want to deal with the cases where code actually fails. Okay, we don't want to deal with the other cases. The other cases are trivial. You say, well, but maybe you have a strong exception guarantee. What does that mean? Well, it means if you fail, then you will restore the program state to what it was before. You are completely transactional. And this is great. If you can have it, it's fantastic. Right? So you try something, it fails, and everything is rolled back, and you have a nice program state. The function, sorry, didn't work, but it was everything it was before. And certainly this is desirable in the library functions. You want to do this in the library function where you have legitimate cases where this library fails, and there you want to say, okay, my library leaves the program in a very well-defined state if the library function fails. But the thing is that library functions usually deal with very little state. So if you have an m-place function of a vector, right, all the state you really have to worry about is the vector. And you have to leave the vector in the same state as it was before. If, say, my m-place and the copy constructors and the stuff that I'm calling there fail, I have to restore the state of the vector. And this is really a little local thing that I can keep under my control. And I'm happy and that you should write write the vector with strong exception safety. Now, this is very hard in application code. Because, I mean, imagine what you have to do. Say you have a chart, right? And the chart has an axis, and the chart has data points, and you are changing around something, so the scaling of the axis changes, and your data points change. And somewhere at the 27th data point, you discover something didn't work, shit. And now you have to write code that rolls back all these changes that you did, and you have huge state, and you have variables that store how many tick marks do you have and what's the extent of your axes, and you have to undo this all, and you have to assume that you can actually undo this all because it requires accessing PowerPoint, and what if that fails again, and then your head explodes. All right. So how do we deal with these things? Well, you say, you know what? We do basic exception guarantee. If we may fail, it's okay. And we will restore the program state, but not to what it was before, but to some valid state. Well, maybe it's a good compromise. We just leave the program in a valid state. We can carry on. Maybe it doesn't require quite as much work, although, yeah, we still are going to have quite a few code paths. And then I'm going to have customer calls like this. Hello, this is Microsoft Word support. Yeah, I was writing a book. Suddenly Word deleted everything. Oh, that's okay. Word only provides basic exception guarantee. Oh, all right then. Thank you very much and have a good day. Okay. I never had calls like that. And that's why this providing the basic exception guarantee also didn't seem to be very, very attractive. And not for the user, at least not for the user part of our code. So, the challenge. Error handling is a lot of effort. In testing, you have many code paths to test because everything may fail. And if you don't test these code paths, I'm sorry, but they won't work. Don't just believe they will work, they won't work. And in development, you have to be absolutely paranoid. You have to check everything. And at the end, what do you have? You have very little customer gain. The customer is not going to have these phone calls with the customer. You're going to work through all your error checks in the... So, what do you do? Now I want to turn the question around. What do you do? Tell me what you do if you're writing real code. What do you do with your API calls? What do you do with your library calls? What do you do with your asserts? Tell me. Tell me, anyone. What do you do? What do you suggest? You must have, every one of you must have a solution to this problem because you have to write code, and this code has to work.
Actually, I try to catch everything and then I log it. If I get to any state which is not valid, I log the state.
Good. Anyone else? What do you do then?
Then I can explicitly search for the cause of the failure.
Okay. What do you do with the program once it logs something?
It depends on the cause. On some causes, I just break the program and just say, okay, stop. I can't work on because I don't have a valid state. And in some cases, I can work with new values, for example. And then I have just to bug fix it.
Okay.
I would say it really depends on what I have to program. If it's an internal tool or something or some private stuff, basically I just crash the program and I don't care. But if it's some servers, then I try to do the thing to log everything so that I can discover what really was a mistake and then restart the service or something. So yeah, okay. Most of the time, if you cannot handle the error because you cannot catch everything, then that's obviously good. But most of the stuff I try to catch.
Okay.
And handle it.
Okay, I think your ideas are not that far away of how we do it. I still want to talk about it. I think many people skip error checking. They basically say, oh, I do this API call, but I don't check whether it worked or not. That is a bad idea. Okay, you should check every single call because it is very hard to find a bug if your call failed and then, like, I don't know, 3 functions down the road, something is strange and you never checked it. So what do we do? We check everything. Every API call. We have macros that check every API call. We have asserts everywhere. The asserts stay in release. And you want, basically with the goal, to keep the program on a very narrow path of correctness. You want to say, okay, as soon as you're going away from this very narrow path, I'm just saying, okay. Now, and really every API call, handle nothing. Check everything, handle nothing. Don't even handle the cases where you think it's easy to handle. Don't handle them either. This is all code that is, it may only be 1 line. Nope, don't write that line. I don't need that line. I don't want that line in my code. Okay, don't handle it. Now, when something goes wrong here, actually think cell phones home. It will prepare a bug report, prepare a core like a stack dump, and send it to our server. And it gets logged there. So we have a big database of all the bugs that occurs somewhere out in the wild. I think some of them, many of them, occur once. 300,000 users, 1 failure. I think sometimes it's just like a cosmic ray that hit the memory. Like, it does have, there are many things that happen only once. Now, what do you do when checks fail? First of all, priority 1 is collect as much information as possible, okay? And send them home. This is priority 1. You don't worry that the user can save his data, that he can do that. No, you just collect data. Why? Because the priority number 1 is to get the bugs that occur out. It's more important that you get information about the bugs than that the user can carry on with his work. Because yes, he can carry on with his work, but he's going to hit the bug again. And there are 300,000 people out there who are also going to hit the bugs. And it's much more important that you are fixing that bug than that the user can carry on. Because the thing is that when you actually carry on somehow, this will kind of get you into the vein of your support department will at some point say, yeah, if you just shake it a little bit and restart and then it will go away. And you don't really want to get into this mindset. You want to get into the mindset, if this thing hits a wall, it just hit a wall. It produced an assert. The assert must go away. Okay, that's the mindset you want in the head of your developers and in your support department. I'm telling them whenever in the log there's an assert, there's a critical problem, everything else doesn't matter anymore. I'm going from defined behavior into undefined behavior land. And if your computer catches fire afterwards, it doesn't matter because you just hit an assert, right? From then on, just hands up, no, nothing happens anymore. What do we do on the server? We halt the server thread. We don't try to restart anything. We want to collect as much information as we can. What's the best way to collect information if you have the server still in that state? Freeze it right there, right? Then I can come in the morning and say, what's the problem? And take a look at it and look at all global variables and look at everything, right? It's like, oh my God, this is the live web server that's out there in ThinkCell. He's supposed to be earning lots of money, but he still stops when he's recounting. He's not restarting automatically, nothing like that. Okay, then carry on somehow. Now, if check was critical, now it's undefined behavior. Suppress any further reports. Whatever. If you hit an assert, that's it. If an API call fails, that's it. You're not reporting anything anymore. This guy went into la la land. Okay? And the only priority is to get that first assert, to fix that. That's your priority. Now, what about the termination on asserts? Never, never, ever terminate when you hit an assert. Never. Get this out of your head. Why? Because asserts can be wrong. Your programmers are not going to write asserts anymore if they get a slap on the hand if the program terminates because their assert was wrong. You want to give people all incentive to write asserts. You want to make people to write strong asserts. You're going to say, I believe this is true here, so I'm going to write this because I made that assumption. And if I'm wrong, what's the consequence? What's the consequence if I'm wrong? Nothing. It's okay. You can make mistakes. And this mistake, if you make that mistake, and that it turns out that you didn't really have to make this assumption, then it's going to be without consequence. And actually, this is a frequent bug. Frequently, the asserts are wrong. Nothing is bad with the program. Just, I overlooked this thing. Yeah, but it still works. Yeah, it's still okay. I have to just extend the assert a little bit. And it is a bug. Fix it. By all means, don't ever live with asserts. Fix them, but don't terminate. Because otherwise, your programmer team is not going to write any asserts anymore. If every time he writes a wrong assert, he gets hit in the head, right? So you want the guy to write strong asserts. Now it's like, but what if you need safety? You need safety. We are running a nuclear power plant. We need safety. We can't just carry on somehow. What do we do? Well, you have to edit. If you're trying to get the safety into the system by controlling the way the asserts are handled, you're doing it at the wrong place. You would need an additional layer on top that says, if my nuclear power plant goes into a critical state, no matter what this guy is saying, I am going to drop the control rods, right? I'm going to shut this thing down. Same thing with our server, right? If our server finds out that there are certain types of requests, say our bug reports, okay? They make the server hang. We already sent 60 bug reports into the system and they never came back. We just counted the number of bug reports that we sent in the system. They have never returned. And maybe they're hanging. I don't know, maybe they're waiting for Arno to take a look, right? At some point, if I keep sending bug reports, at some point, not only the bug reports are going to stop, but my user front end is also going to stop because we ate up all the threads, right? That's a bad idea. So we basically say that if there is we count the types of requests at a pretty high level and say if there are too many threads are busy with that kind of request, just don't take these kind of requests anymore. I think there's a bug in there. And they all hang. And in this case, it also doesn't matter whether you have an assert that goes to an infinite loop or whether you just happen to program an infinite loop. I mean, that's also possible, right? It's not the only problem that can occur is that there's an assert and it goes into an infinite loop. It also could just be that you just programmed an infinite loop, right? And you also want to be safe against these kind of problems. So if you need safety, add them at a higher level. Don't try to do it in the assert. Now then, you reproduce the error in the lab, and you only add code for errors that are reproducible. Otherwise, everything else is guessing. If you write a handler for an error that you cannot reproduce, you don't really know why this error occurred, why you don't understand why it occurred. And you probably can make a half-assed attempt at kind of trying to, yeah, maybe. So I would be very careful adding code for errors that are not reproducible. You can't even test the error handler, right? That's the other thing. I mean, if you can't reproduce the error, you can't reproduce the error handler. So what does this approach lead to? And this is basically what I want you to take home. And I think the programs get better that way. 5% of the handlers, or 5% of the API calls, cause the errors that cause 95% of the errors. 5% of the API calls, I should probably say, cause 95% of the errors. And you need to write handlers for these. So our program is full of handlers that make the error disappear. We found out this API call, when calling PowerPoint, gives us an error. But if I try again, or if I put on a pink skirt and dance the hula hula, then suddenly PowerPoint will behave. And then it works, right? And sometimes you have kind of these situations where you don't really know why it produces this error until you actually have a reproduction. And then suddenly it all falls into place, and you can actually produce a program that doesn't fail. The user never knows that you hit an error. And that's the best error handling you can do. Because then also, you don't have to pass out the error down below. You don't have to tell your caller, sorry, didn't work, right? But you can actually make it work. And often there's little alternative. If you want to make the user happy, you better work. And this keeps your program much simpler, because the callers don't have to worry about it. They just call the function and say, this function works. And then you have to work as long as you can to actually make it work. And this is really time well spent. This is how you spend the time on the errors that actually occur, and that makes your program more reliable. It doesn't make your program more reliable if you write error handlers where you don't know whether they ever get used or not. Don't spend your time doing that. Spend time on working on a good logging. Spend time on error reporting, on a database, on whatever you need. We spend a lot of work on that. And I think, but we didn't spend time on writing error handlers. We spend time on error handlers when we actually have an error. And hopefully this is an error that then just will go away because we solved the problem. I want to be a little bit more specific. Okay, I got my main message home. I want to be a little more specific about what kind of errors can occur and what am I doing about it. Now, and this actually gets refined, and this is the result of our years of doing this. And it actually makes sense to categorize them. It makes sense to give them kind of a severity. And I want to go through our severities, our categories, and maybe you can adopt them for you, or maybe you can see for your applications what you are having. The worst category of errors is you are pretty sure that your program is not going to work as intended. If you make an API call and the API call fails, likely the program is not going to work because you made that API call for a reason. It's not like you didn't care about the API call. If you didn't care about the API, you wouldn't make it in the first place. So what do? Well, in that case, you tell the desktop user, hey, I have an error. I have an error. And the important thing is the false alarm is very unlikely because, I mean, it's an API call. You just probably you're going to crash, right? Even if you check for a null pointer access, the thing that's next going to happen is it's going to crash for sure. So you don't have any false alarms, and you increase the chance of getting more info because you are going to tell him, stop, right? There's an error. Please give us more information. And so this is basically the worst category. If asserts do not fall into this category because you don't really know whether you have a wrong assert. right? API calls that fail, they fall into this category. Asserts don't. Now, do you have well-defined program behavior? Well, after an assert failed, you didn't. You don't. But you probably don't want to put up an error message. Well, why? Well, again, you don't want to tell people, hey, if you're writing an assert, you get error messages popping up left and right. So you probably don't want to tell the user that you just an assert failed, just in case you have a wrong assert. Our server, on the other hand, goes into an infinite loop, okay? Because this is undefined behavior, and we can afford it. And we want to fix the problem. We want to, remember, priority one is collect as much information as possible. This collides here a little bit with don't allow your people to write asserts that fail. If they do this on the server, I mean, they can go there right away and fix it, so that there's the much easier to have the appropriate response. Now, this is the line of this is undefined behavior, this is defined behavior. The program is not really in a bad state. And there are surprisingly many scenarios where the program is in a good state, the program is in a valid state, but you may still want to do something. Let's look at them. Sometimes you have conditions that you think they have never been reproduced, but theoretically you can handle them. What's an example? You are providing a function for PowerPoint. PowerPoint wants to do stuff. And it uses a published interface, and that published interface may return errors. It has in its defined behavior description, it has, if you are out of memory, just return out of memory. So okay, I'm writing my interface, if I'm out of memory, I'm returning out of memory. Now, well, in all likelihood, PowerPoint is not going to like if you report, sorry, I'm out of memory. Bad things may happen. Now, let's say you can't reproduce that scenario. You can't come up with a scenario where this thing actually returns out of memory. There, you could say, well, the condition itself is defined behavior. I mean, I'm doing something according to the specification. But I've never really tried out my caller with that specification. I never really tried doing that. And I don't really know what happens. I would like, if someone has a reproduction, I would like to have it. And this is this kind of thing. Condition has never been reproduced. Now, the server sends a report. It carries on, but it sends a report. And if I'm encountering this, then maybe I can decide, okay, maybe I strengthen this to an assert if I really don't like it, or I can at least take a look at it. Now, the debug build actually produces an error dialog because in debug it means, hey, this is my developers running it. Oh, I've just found a repro for this very unlikely scenario. I want to know about it. I want to now investigate what actually is the consequence of encountering this situation. Okay, now if that's not the case, if we know we have the condition reproduced, there's another thing. Is the user experience good? It could be that we have a third-party bug, something that we didn't work completely around. You say, okay, you got I don't know, Google Desktop installed, and Google Desktop messes up your calls, and you know that you can't do certain things if Google Desktop is installed. And Google Desktop is installed on quite a few machines, and I'm saying, well, I know the scenario. I installed Google Desktop on our machine, and we can't afford to completely crash because too many people have it. But there are certain things that may not quite work. It's kind of okay, it works, but we can't make everything work if this thing is installed. We can't work around the problem entirely. Certainly, you want to log this thing because the user, you could put up a dialog saying, I'm really sorry you installed it, please fix this problem. Maybe it's something that's relatively rare, okay? And you kind of don't want to waste too much effort on writing error dialogues and please do this and please do that. Blah, blah, blah. What's the minimum you should do? Well, the minimum you should do is write it into a log because the user is going to call and say, oh, my PowerPoint is broken, what did you do? And then you can look into the log and say, but you encountered this bad situation. Don't be surprised that your PowerPoint doesn't work. I don't want to hunt for that you had this particular scenario on your computer. I don't want to hunt for it. I want to just be able to look at the log and say, yep, there it is. You got this particular situation. So you want to log this. One level further down even is you have a situation that we worked around completely. We have actually encountered the situation before, but it is a little bit strange. It's an indication that the user has something bad on his system, something fishy on his system. Now, you want to put up, when you are for the desktop user, you want to put up, during the remote support session, you want to put up a dialogue. So if the user, basically, if your support attaches to that thing, you want a dialogue saying, this is a system that has this bad scenario. Now, maybe this sounds a little bit abstract. I'll tell you what it is. You are hooking a function, here, Simon style. And you found out that there is already someone else hooking that function. We can deal with that. We're robust against it. It's expected behavior. It's fine. Does the user have any bad experience? No, theoretically not. If everyone's doing the right thing, everything is fine. Everyone can play together. Nothing to worry about, really. But if these guys did something wrong, the program will crash. You don't know whether these guys do it right or wrong. But if the guy calls you and says, something doesn't work, you basically want to call out to the support guys everything that is kind of weird. And these are exactly these conditions where the program is weird somehow. The environment is weird. You've got some behavior that is not the usual thing. It may be supported, and as far as you know, you can completely work with the situation, but it may be an indication of other trouble elsewhere. And that's this thing. It's different from here because really the user scenario, the user behavior, and the user experience is still good, right here. But maybe we still have trouble elsewhere. Not at this particular point, but elsewhere. And this is just a symptom. Okay, now we're getting less and less hard in our scenarios. If you have a situation that doesn't occur in every run, in every code path, maybe you still want to log it when you have a remote support session. You won't want to put up a dialogue or anything because it may be completely okay. But if you really want to diagnose what the program is doing, you may want to log this thing. Just for at the end, you can look at the diagnostic, see was there anything unusual. And this log already gets long, right? This is already there are many situations where something is wrong. But there are sometimes situations that occur in every code path, and there you shouldn't log. For example, I iterate until I hit the end, and the end may be an error condition, right? Maybe out of elements. The API call returns out of elements. This is not something you need to log because it will, every time you're running through this loop, at some point it will be out of elements. So you don't want to clog your log with these kind of error conditions that occur on every single run of the function. That doesn't make a whole lot of sense. All right, I'm done with that. I hope that helped a little bit, and maybe you can think the ways that you are handling errors. I want to do one more thing, and then I'm going to be done, and you guys can go to dinner. How not to handle a particular class of errors. So you got a 32-bit int, that's 2 billion, and you add two of them together. What's B?
Minus something.
Okay, anyone else?
Undefined behavior.
Undefined behavior. Okay. Now, what does that mean? What does that mean?
You could, in theory, have a system which doesn't have tooth complements. And
Okay, that's okay. So we have the basically on a tooth complement system you're going to get something minus la la la. On a non-tooth complement system you're saying yes, you could have that. You will get something else after the overflow. And then there is this undefined behavior thing that was going around here. Again, the question, what's undefined behavior?
Undefined behavior means that you can't possibly say on every system you run this code, it does the same thing. And so if you have a two-complement system, it will do this.
That's not undefined behavior.
Undefined behavior might crash, erase your hard drive. In theory. So you just don't assume it.
Does it here that we just say we don't care what happens now? We just say we can control this, fine, do whatever we want.
Okay, this somewhere there it comes close. Basically, you can, after you had undefined behavior, and this is undefined behavior, it wouldn't be if you have an unsigned int. An unsigned int requires modulo true arithmetic. That's why I want to give you, just as a last nugget, I want to give you this. If you're adding two ints and they overflow, this is undefined behavior. And that has consequences. What's undefined behavior? Undefined behavior means your program could do anything. It could format your hard drive. It could do anything. Anything. You can't check for undefined behavior because you may not get the check executed. The compiler can do anything. This in particular doesn't work. Even if you have two's complement. You can assume two's complement all you want. You have an Intel system, you know your system, it's all fine, it's all good. Still, the compiler will say, if you have a number and you're adding this number with each other, you have double the values, and then B can't be less than A. It is impossible that this actually occurs. This is never the case. And if I overflow, it's undefined behavior. And undefined behavior, basically, I don't write code. I don't generate code for undefined behavior. This will get dropped out of your compilation entirely. So this will run, you think you check it. No, you don't check it. It doesn't work. There is no way you can check for an overflow because an overflow is undefined behavior. You have to check before you overflow whether you're going to overflow. If you're overflowing, game's over. Your program is, this happens. This is not theoretical. This is something that happens because the compilers get better and better at optimizing code. And they will actually exploit these kind of things. They will say, oh, this can't happen in the first place. It's impossible. Because the programmer knows that because it's undefined behavior, right? So it doesn't overflow. So I don't need to execute this. Well, actually, if he sees that this is undefined behavior, he could erase it all. You have 2 billion and A plus A. If you have an if up here and that does this, the compiler could say, this is guaranteed to produce undefined behavior. I'm not even going to compile it. Just throw it out. It's just the whole addition never happens, right? So be darn careful about undefined behavior. This has bitten us. It will bite other people, okay? Thank you very much for attending.